Hello and welcome to my lab. Today here on the bench we have a DX 5000. This radio is really wide propagated here in Germany, so there are really a lot of units in the market. This radio is sold under different brands all over the world. Well, here, as I already said, it is sold as DX 5000 from Maas, but it is also well known as Alpha 10 Max or as Contax CS1000DX or as CRT SS 6900, as Intex HR 5500 or as KPO DX 5000. So we have really a lot of brands where this radio is sold under, and well, so it is really a well-known radio in the market. Also, it is not that old, so it is a quite newer brand, and production, as far as I know, is in China. Well, this radio came in with having trouble on upper sideband, so it is not really possible to dial the frequency in with the clarifier, so it is still a little bit Mickey Mouse sound, and yeah, as the owner said, you can't really adjust it with the clarifier. It is the same on TX or on RX, so both directions same problem. He said also that on LSB it is much better, so you can use it on LSB, and you can use it on FM and AM, but always trouble on upper sideband. So that is what we need to investigate. If it is only on upper sideband, it could be a wrong aligned carrier oscillator. If it is on all the different modes, then there must be another issue. But also this radio is known for having some trouble with the local oscillators, so this radio is fighting with some instabilities, especially the earlier models, which this is from, so it is also an earlier model, and so that could be a reason that we have really instability in one of the local oscillators, and that is what we need to figure out. So, well, follow me along the troubleshooting and the repair, so that we will have at the end a nice working radio. Well, as always, let's check if we have the same finding than what the owner has told us. Well, the radio is now warmed up, so it runs now for half an hour or a bit more, and I have already connected it to the signal generator, and it is set to upper sideband on 28500, and what we want to check is if the radio is really in the frequency or if it is off. Well, the parameters which are seen in the camera are most important for us. First of all, of course, we are sending with minus 73 dBm to have a strong signal at our receiver input, and then of course our frequency, and due to the fact that we are on a single sideband, we are feeding in 1 kilohertz higher than the radio is set to. And well, when we now feed back the frequency back to the communication tester, we can read here the audio frequency which comes back from the radio. And what we can see here is that we have a frequency error of about, yeah, let me say 87, 88 Hertz. And 88 or close to 90 Hertz is definitely to be recognized on the radio bands. So if this error is that high, you will definitely hear it. So let us check what it will be on the lower sideband, and therefore let me change our frequency to 499, because now we must go below our dialed in frequency on the radio. And I now switch the radio to LSB, and now what you can see here, it is 22 Hertz off, so that is much less than what we have seen on upper sideband. So there's a difference, and 20 Hertz might be okay. So that is the tolerance what all different and much more expensive radios also have. So 20 Hertz is more or less okay. So well, yes, we could tweak it a little bit, but basically I would say that is okay, no problem whatsoever. And well, then let's simply check on FM. FM we will check on transmit, and let's see what we can see when we put it into transmit. And this is now the transmitted frequency, and you can see radio is sending with 41 watt output. And what we see here is, yeah, nearly exactly the same what we have already recognized on lower sideband. It is approximately 20 Hertz or a bit more off, so that is the same picture to us. But I mean, on FM it is much different. So the frequency could be much more off, and you wouldn't recognize it. It is always critical to have a frequency drift on SSB, because you really recognize very small steps. Okay, and let us do the same on AM. So now I've switched it to AM. You see that is here the dead key, 11.5 watt. And again, it is, yeah, somewhere between 20 and 30 Hertz off, so we could measure it a bit more accurate, but that is not necessary for our first test. So what we can summarize is on AM, on FM and on SSB lower sideband we have something between 20 and 30 Hertz off. We know on AM and as well on FM it is completely okay, because you wouldn't recognize this frequency shift, but on upper sideband and or generally spoken on SSB, it is much more critical as if the frequency is off, and that is what we can see when I go back to upper sideband, and we gonna now check it again on receive, because it is a bit easier. So let me go to 25001, because then our frequency which gets feeded back should be exactly on 1 kilohertz, and you recognized while the radio is warming up the error is increasing. Now we are 95 Hertz off. I mean, our signal itself looks pretty nice, so it is a nice and clear sign, so no problem whatsoever. But yeah, I mean 90 Hertz off is a problem. And what you can see as well, we have only a SINAT of about 10 dB, and that is far too bad for this radio with input level of about minus 73 dBm, so that is very bad. So that is as well a clear indication for that the frequency is off. And have a look, it is still increasing. Now we are already about 100 Hertz off, and so that seems to be the increasing temperature. So with the temperature creeping up, the error is getting bigger. So that is a clear finding. Well, now I'm interested if I'm able to change the picture on our audio frequency feedback by simply adjusting the clarifier. And the clarifier is set to 10 kilohertz steps. So when we are let me say about 10, so that means 100 hertz, the setup is put to 100 hertz, then the frequency on our frequency counter should be nearly around 1 kilohertz, and then we should have as well a very good SINAT. So that is what we are gonna check. So I will change the clarifier setting, and we will watch while I'm doing it. We will watch our instrument. Well, okay, so I hope you can really see all the instruments, and again we are now at 124 Hertz, so that is really too much, and that is definitely something you hear on the radio, so that arrow is really not good. And as I already said before, now we are down at 7.2 dB synod, which is as well a clear sign that something is wrong. And let me now change the clarifier in 10 Hertz steps, and let's see if we are able to change this this arrow. And we are, our arrow is now 120 and it goes up to 130. And if we are able to clarify this arrow while this frequency is going down to 1 kilohertz, this here, the synod should go up to, let me say, something around 30 or a bit more, 31, 32 dB. Then if we reach 30 dB here on this meter, and if we are back here of to around 1 kilohertz, then our frequency arrow is gone. So let me start right now. So 10, 20, and you can already see something is happening. 30, 40, 50, 60, watch this, 70, look here, 80, arrow is getting smaller, synod is increasing, 90, 100, look here, that is nice, and 29 Hertz off, so we are now with a clarifier at plus 100 Hertz, now 110, 120, now our arrow is only 8 Hertz, and we have a very nice synod. Let's see if when we go to 130, 130 is a bit too much, so let's go to 120, and you can see now we have the arrow at, it is 8-9 Hertz with a very nice synod, and this is a very good setting for the radio. So that means, let me go down here to the radio. Let me check if this is easily to be I can manage it very easy. And what you can see here, so that is what I have already said. Now our clarifier is on 120 Hertz plus, and this clarifier correction simply reduces or eliminates the arrow. Let's go back, so you can clearly see that we only have 8, 9, 7 Hertz off. So that is a clear indication that we have an alignment problem with our radio. So that means one of the carrier oscillators, so in this case of course the carrier oscillator for upper sideband needs to get a new alignment. That is what we will do, but you know, I'm a little bit unhappy with what we have up to now, because you know, the first time, let me go a little closer, the first time when the radio was cold, and when I switched on the radio for you know, warming up, I have recognized, therefore I put my oscilloscope to the radio, and the first time when I switched it on, I have seen that we had a frequency jitter, and we had a frequency jumping between 200 and 400 Hertz. So when I say 400 Hertz, here we had a jumping frequency between 200 and 400 Hertz, and that is also a known fault, but for the moment in time it disappears, and it is not there, so it totally vanished. So I do not know what it was. Was it only during the warm-up period, or is it still a fault which is hidden for the moment in time? So I think I need to let the radio completely cool down, and when it is completely cooled down, I need to do the same as I had done it before. And yeah, if we have then again a significant frequency jitter and jumping frequency, we really need to investigate the local oscillators a little bit more in detail. So maybe that there is also this frequency instability, and that needs to be checked out. But for the moment in time, we can say that the radio needs alignment for one carrier oscillator, and what you see is 6 Hertz off, so that is good. So okay, next step, I let the radio cool down, see if I have the same finding when it is cold, and then we decide what we do next. Well, meanwhile, let us have a look into the block diagram to understand a bit more what's going on. So basically we have two points of interest. So that is first of all this area, and secondly this area. Okay, so let's zoom in a little bit up here, so that we can hopefully get the idea. So this here, the Epsilon 300, is our reference oscillator, and this oscillator is doing two jobs. So first of all, it is the master or the reference oscillator for our PLL circuit, which is at least adjusting the VCO, which is sitting here, and will then go up here to our first mixer. So that is the first what this oscillator has to do. But secondly, beside that it is the master oscillator for the PLL, it is as well the reference oscillator for our second local oscillator as well. So that means this 10.24 megahertz is very important, because only if this oscillator is working properly, the PLL, the VCO, and of course the second LO is working in a right way, and therefore that is the first what it is very important. But all our investigations before shows that this oscillator seems to be more or less okay. So it looks like that we do not have a big deal with this oscillator, because otherwise we wouldn't have this little arrow in AM and FM and so on. So that means most likely this oscillator is okay. But anyway, we gonna check it. And then secondly, we have this, let me see how we can get it in a little bit better. Yeah. Secondly, we have this Carrier oscillator, and this Carrier oscillator has to deliver different frequencies depending on the mode which is switched in. So for instance, for FM, this Carrier oscillator has to deliver exactly 10.695 megahertz, and then here we have our mode switch, and with the mode switch this Carrier oscillator gets tuned a little bit, and I'll show you in a minute how it really works. And then for upper sideband, this has to deliver 10.6925 megahertz, and of course for lower sideband it is then again a different frequency which this local oscillator has to deliver. So for LSB it is 10.6975, so that is the shift you need to operate in upper sideband and lower sideband. And in let me see where I have the schematic for it. Here it is. Let me see that we can all really see it. So basically what you see here, this is a Carrier oscillator, and you see the shift of the Carrier frequency happens by putting some DC to this varactor diode, and with this varactor diode you can change the frequency which is needed to operate in the different modes. So that is how it is working, and we have a mod what we will do to make this oscillator a little bit more robust, and that is to change out this resistor here, which is currently 56k ohm resistor, and we will reduce it to a 33 kilo ohm resistor, and that makes the oscillator a bit more robust, and then we will hope that finally the alignment we have to do, that is for sure, because we have seen the error which is caused by this oscillator. So we have to do our alignment, but first of all we do this modification to make this oscillator a bit more robust. Okay, so this is now the look inside our radio, and you see it is all surface mount technology down here. So you really need the right equipment to do any repair on a board like this. Anyhow, so what we have seen in the block diagram and as well on the schematics are the two oscillators, and this here is our main or reference oscillator, which is responsible for our 10.24 megahertz. So for, as we have heard before, local oscillator and the VCO. And secondly, this here is our carrier oscillator, and what we need to do is to change out this resistor down here, which is the 56 kilo ohm version, and we convert it into the 33 k ohm resistor, and this here is the quartz. And normally what we normally would do, so normally we would go down here, because there down below is our test point, and let me see if I can show it to you. So now that is the signal out of the carrier oscillator, and normally I would connect the frequency the frequency counter to this test point, and then adjust our different carrier modes, so for upper sideband, lower sideband, and so on. But as this is only a normal quartz, which is down here, so this is the quartz which is responsible for it, and due to that, because you know, it is only a quartz, and only by opening the housing, the inner of our radio cools out again, and that means the frequency is drifting only by taking off the cover. And I have recognized that the drift is changing, or the frequency is changing by simply taking off the cover, so it is 20, 30 or 40 hertz. So that is alone the cover which is also covering the heat inside. So it is not a good idea to do the alignment by, you know, open housing. You never will really adjust your frequency in a way you need it. But first of all, let's do now our modification, and you see here in my hand I have this really tiny resistors, and this is, as you can see, a 33 kilo ohm resistor, which we have to fit in the circuit, and therefore well, you know, there are really different methods of doing it. So you can do it by example using two soldering irons, and can go down to the resistor, heat both sides, and then take it out. So that is definitely one method, but I prefer to do it with hot air. So I will heat the area a little bit until the solder is melting, and then I will take out the resistor and replace the new one. Well, but you know, as this is really so tiny, it is not a good idea to do it through the lens, because I do not have the right position to really do it good. So therefore, let me do it, and if it is done, we go ahead, close again the housing, okay, and then do our alignments from outside, because I do not need to turn any coils, as you may have seen it before. So to change the frequency of this Carrier Oscillator simply happens by adjusting the microprocessor, because we adjust the DC voltage for the varactor diode, and that is to be done by changing the DC over the microprocessor. So that is a procedure. Okay, so modification is done. What I want to check right now is the test point 500, which is at least frequency out of the VCO for or from our PLL circuit, and here it is. So that is the frequency out of the PLL or out of the VCO, and if we gonna change now the frequency, let me see if we can read it up there. So yeah, first of all, it is clear that we want to see a nice sign what we do, so that is important to check if there is not too much distortion on the signal, but it is not, and so that is good. That is what I wanted to check, and here we can see the VCO frequency. It is not able to bring it into focus. I think though that is good. Now when I change the change the channel, you see the frequency moving, right? And that is exactly what we want to see. So that is working, and still we have a nice sign, so no problem whatsoever. That means from that perspective it seems to be okay. So okay, so there is another checkpoint as well, so let me go down here. Will I be able to demonstrate it here through the lens? I do not get good ground to show this measurement. So this is a 10.24 megahertz oscillator, but it is really difficult to demonstrate Okay, here it is a very small signal, but it shows that the 10.4 megahertz oscillator is working, so you can read the frequency 10.40, so it is very accurate, so we do not need to worry about this. So now I'm gonna close our housing, as I said before, because simply by heating this oscillator we get in an enormous drift, and we need to close the box to get it under control, and then we do our alignments. Okay, and I wanted to be sure that we have the same on transmit, so I opened the microphone so that I have access to the audio wire, and I have connected my audio generator to the microphone wire, which is the audio wire at least, and well, I'm putting 1 kilohertz here onto it, and I'm on upper sideband, and the cover is on, so radio is close, and we hopefully have a constant temperature inside. And now I have adjusted my, let me see if we can read it, I have adjusted my frequency counter to it, and when I'm now keying the radio, so what you can see is that we are 110, approximately 100 hertz off on upper sideband, so that needs to be aligned. And when I switch to lower sideband, which I have done now, and have a look, now we are 68 hertz off, and it is a bit less than what we see on upper sideband. So now radio is hot enough, and now let's start our alignment procedure, that we get rid of the error. Okay, so now let's set the radio into adjusting mode to have access to the processor. So therefore we want to press function button, switch the radio on, and then these two buttons, and what you can see right now here is the adjustment mode, and what we need to do right now is to do the adjustment by changing the clarifier. Okay, upper is indicating we are in upper sideband, and this is the basic alignment. Now we will see our frequency counter, and we go into transmit, and we adjust with the clarifier our output frequency approximately 100 and yeah, what was it, 120 hertz higher. So let me adjust it higher, and you see that the setting is changing. Okay, so we are getting closer. So that is 3 Hz, and that is 2 3 Hz. So somewhat around that point. Okay, so that means we are here on 155. So now let me simply switch the radio off. Now I'm back in normal operation, so I shut it down and switched it on again. So now we are back on our normal frequency where we were adjusting it. And when I now key the radio, we should read the right frequency. So let me check it if we have what we want. So remember, we should read 28501 if everything is right. So now I'm keying, and yeah, have a look. So now we have 1 or 2 Hertz off, and that is absolutely fantastic. So we do not need to do any more. So upper sideband adjustment has been done, so you can clearly see it is working, and yeah, it is clear that it is always drifting a little bit, but as I already told you before, it is depending on the temperature inside, and it is clear if you have a heavy operation, the radio gets more hot by the final stage, because the final stage under operation is producing a lot of heat. So that is simply the reason why you have heat sink. And yeah, so that's it. I mean, I will do, of course, now lower sideband and FM and AM. I will do it as well. But anyway, you have seen the procedure, how to do it. I mean, as I already told you, normally you would connect your frequency counter directly to the oscillator. But remember, if I take off the cover, then the temperature is changing, and we never would get the right setting by reading the frequency counter, because when I then put back the cover, operate the radio, and then we have a drift again. So now I have done it on another way. I mean, yeah, it is a little bit more tricky, so you need to really look a little bit right and left, but basically this method is more reliable. And remember, we have done the modification to make this Carrier Oscillator a little bit more robust. And yeah, so that is what I wanted to show you. The same procedure we have to do with lower sideband FM and AM, that is for sure, but I think I do not need to show it. Also, again, the same procedure you've seen. I hope everything you need to know to do this by your own. And therefore, I'm at the end of my little video. Thank you all. Thank you all that you are still here and listen to my video. And yeah, if you like it, please give me a big thumb up, and catch you next time. Bye.